All right, section 13.8 is called Constrained Optimization and Lagrange Multipliers. I know that looks like Lagrange. It's Lagrange. So we're going to take a look from an intuitive perspective first at what this is doing. So I want you to imagine you're going to the mountains and there's a mountain range. So what we have been doing so far, basically in the last section, is one of two things. The first thing we did is we thought about the whole mountain range, and we looked for places where we had the highest points, the lowest points, and then these points were sort of, it was the highest in one direction, lowest in the other, right? That's what we've done. The second thing we did, the very last thing in 13.7, was we looked at sort of saying, okay, but now we're only looking within a certain space of the mountain range. We don't want to go everywhere in the mountain range. We're sort of confined for some reason, right? There's fences up or something like that. So we're confined to this area, and we're going to look along this confined area for where we have the maximums and minimums. All right, so this section has the idea of there being a road. Okay, so you're actually on the road or on the trail if you want to be on a trail, okay? You're not deviating from the road or the trail. The question still remains the same. Where are you at the highest or the lowest point? But along the trail now. And the trail is not necessarily a specific equation that's very nice and friendly, like we had x equals to y, or x equals to 2, like we did in the constrained equation from the last section. Okay? So do you kind of get the picture of the difference? We've got this other area that we're trying to get really, we're trying to be on the road or on the trail or whatever, and we want to find the max and min along that curve instead of being along the mountain itself. All right, so there's a way to think about that. And what we're going to do is, the way to think about that is actually with Lagrange multipliers. So the methods in 13.7 are only part of our discussion of optimization. We will use, and I'll define what they actually are, but what we're going to use is something called Lagrange multipliers. Next. And we're going to do this a little bit differently than I normally present for you. We're going to actually do a problem while I'm explaining the process so you can see all of it at the same time. We're going to give this a different kind of a feel. So the example we're going to work with as I explain this says use Lagrange multipliers. I promise I'm going to define what that actually is. Maybe not today, though. Lagrange multipliers to find the closest point on the curve to the indicated point. Our equation, our curve in this case, we're actually going to look at a line to make things simple to start with, and a point not on the line, 0, 2. So for starters, we're just going to draw a picture of what this looks like and kind of imagine what this might have for its solution, and imagine a way to find the solution that we're looking for. So we've got an equation, x minus 2, which would be a diagonal line, like a slope of 1, and then crossing at negative 2. So something like this. And we've got the point that we are being given, which is 0, 2 up here. So we're trying to figure out what point on this line is the closest to this point right here. So this is not a complicated sort of picture. What do you imagine we're going to have to do? It looks something like a Pythagorean theorem. You're not far off. Distance formula is how we're going to actually think of it, but that is a version of the Pythagorean theorem.
It has to be a line that's perpendicular to your line.
And that's really important too. This idea that basically what we want is we want to find the shortest distance to this line, right?
So the reciprocal slope.
All right, yeah, so with lines, this works really nicely. Yes, we can talk about perpendiculars and things make a lot of sense. It doesn't work quite as clean if we didn't have a line and we had a curve. But we have this same idea that somehow it needs to be perpendicular in some sense, right, for this to actually work. All right, very good. So let's write down a few of these ideas. You're going to see several of things that you're describing come about in what I'm going to write, but just to sort of give a picture of what's happening. So clearly, we want to minimize distance. To the point 0, 2, we'll say that way. And the distance would be given by what equation? How can we find the distance? Yeah, so we want the square root of the distances here. So we want the distance between x on our curve and the point 0, 2. So that's just x minus 0 squared. And we want the y on our curve minus the y value at the point we're talking about, which would be y squared. Y minus 2 squared, excuse me. I wrote it and said it wrong. But here's the catch that makes this really nice. But this will be minimized exactly where x squared plus y minus 2 squared is minimized. Okay, so what did I do? I removed the square root, right? Why would I want to do that? Radicals make it harder to take derivatives, right? They're more complicated. And for what we're doing, they don't provide anything new in terms of information. They're not going to give us any additional maximum or minimum values, anything like that, so that they're inconsequential for what we're doing. So we're ignoring them, basically. We're choosing to ignore them for the purposes of this problem. It's the beauty of mathematics, right? And so, as I just said, and this is easier to work with. All right, so now we're going to kind of enter into what James had mentioned when he observed this. The closest point... Oh, you know what? Let me stop actually there and talk about this. What is this an equation of now without the square root? Do you know? Circle. It's a circle. So if you imagine, and I'll try and draw one at least a little bit in here. We'll see how well I can do with it. No, it's not a circle. Change my image.
Circle squares.
Circle, square, you know. That's not too bad. So you imagine actually taking this circle, instead of thinking about the distance of it, you can think about the radius. I mean, the distance is the radius of that circle, right? So you can actually think about that circle. What can you tell me about the circle and the line? I mean, I've drawn them in a very specific way. How have I drawn them? Tangent. I have drawn them tangent. Okay, so the closest point will be where the circle and line are tangent. And here's where we're going to be using what you guys did back in section 13.6, the one you did for homework last night. Since the gradient, remember that's the vector formed by the first partials of each of them individually. Since the gradient of a function is orthogonal, right? That's that perpendicular that you mentioned, James. Orthogonal to the level curve at any point. Then the gradient of the curve f and the, okay, I need a little more space, give me just a second. And the constraint G must be parallel. Hence, the gradient of f equals some multiplier times the gradient of G. I'll write that bigger to the side. That was too tiny, isn't it? The gradient of f is some multiplier. That is a lambda. That's what we're using. Times our constraint function, g of xy. I'll define it formally in a moment, but this lambda, that's a Lagrange multiplier.
Sounds like a disease.
You know, it sounds like a disease. Yeah.
Do you put that gradient symbol down in the one in the corner?
I do. Oh, I'm missing it up above, though. You're right. Thank you. That's what happens when you rewrite things. They might disappear. All right, make sure you've got that gradient symbol in there. Thank you, Jordan. I appreciate that. Okay, so the gradients are parallel, which means that they are multiplicative factors of each other, potentially. Okay? All right, so let's actually finish this problem with that idea. All right, so we have our function. Our function is this circle that we're working with, okay? So our function f of xy is x squared plus y minus 2 squared. And our constraint is the part at which we are actually constrained. We have to stop. The circle can sort of be large or as small as we want, and we're going to want it to stop right when it hits that point on that curve. So that's the constraint. That's sort of our point beyond which we cannot go. All right? So that's g of x, and that's going to be, let me actually show you how this works. This is y equals x minus 2. All we need to do is we need to get everything on the same side, and that will be g of xy. So you can move x to the right, you can move, x to the left and 2 to the left, you can move everything to the right. It doesn't make any difference. It's going to, because you're going to be factoring and figuring out a multiple of this anyway. So I'm going to move it like this to say x minus y minus 2. But if you move it the other way, it'll be fine. So this is x minus y minus 2 is my constraint equation. And then what I need is I need the gradient. All right, so draw upon your knowledge from 2 days ago and yesterday and maybe right before class, I don't know, whenever you finish that homework up. Gradient, what do I have to do? Yeah, so this is f sub x, right? And then f sub y, right? And it's a vector that's formed by taking those partials. So, using this equation, what is f sub x? 2x. What is f sub y? It's 2y minus 4. Does that sound right? You can either distribute out that y minus 2 squared, or you can use a chain rule and bring your 2 down and then multiply by the y minus 2 inside to give you the y minus 4 when you distribute it, 2y minus 4. All right, g of xy is easier even than that. The gradient of g, what is it? 1 and -1, actually, yeah. All right, so what we found out in the last page, the sort of the highlight of that page was that last equation that said the gradient of f at xy equals lambda times the gradient of g at xy. That was the point of me writing all of that work down, was to get to that conclusion. So we're going to use that with our function. And in particular, the easiest thing to do is to do it component-wise, right? I mean, in order for this to be equal to this times lambda, it means that each of the components equals each of the other components times lambda. So when I create this and I say the gradient of f equals lambda times the gradient of g, it's equivalent to having each of the components be that way. So my 2x is a component, the x component, and then my other one is lambda times 1. So the other one then would be the second component of f, gradient of f, which would be 2y minus 4, and then I've got to equal lambda times the gradient of g, which is -1. We're super close to being done, so bear with me for just about a minute more. All right, using this information, we know that lambda equals to 2x, right? So into the other equation, I can put that information. I've got 2y minus 4 equals -1 times 2x, or -2x. And I end up having then that y is equal to -x plus 2. Okay? So you might feel like, well, now what? Well, you plug this into the constraint. So you substitute this into the constraint. So the constraint up here, before I solved it, set it equal to g of x, was y equals x minus 2. So I plug in this equation. So y is x minus 2, and this one says y is -x plus 2. So I've got -x plus 2 equals x minus 2. What would x have to equal to make that work? Solve that for x, in other words. Might be able to eyeball it even. 2 is correct. If you solve this, you get x is 2. All right, but if you plug in x equals to 2 into that constraint equation, what will y equal? If x is 2, y is equal to 0. So the closest point is at 2, 0, which does in fact lie on my curve. I know it does because that's how I found the other component, 0, of the ordered pair. Okay, so I'm going to write down the homework for this section because the first couple of them are like that problem. You could at least make progress to do those two over the weekend. I won't collect it, of course, on Tuesday or anything, but let me write this down for you. The homework is page 894. 2, 5, 8, 10, 13, 16, 19, 43, and 44. Obviously, the later parts we haven't gotten to.